So with this, we will go to our next presentation from University of Washington, developing pre-stressed concrete girder cross sections for longer spans and new materials. Hank Knight is going to present it on behalf of Dr. John Stanton. Hank?
But yeah, so my name is Hank Knight, and I'm a graduate student who's been working with Professor John Stanton and Professor Richard Wiebe for just under 2 years now. And on our project here, we're looking at developing pre-stressed concrete bridge girder cross sections that would be suitable for even longer pre-stressed concrete sections now. So as I mentioned, our main goal is to see if we can come up with new girder cross sections or even potentially modified cross sections that work well for long span pre-stressed concrete girders. And additionally, a kind of a sub goal within that is if we have our current cross sections that are used on long span bridge girders, where do limits exist in terms of length and performance with those current cross sections? And as we're doing that, we want to make sure that we are, evaluating these girders with as few simplifying assumptions as possible. So we want to be able to be looking at lateral instability, considering, as many, complicating factors as we can to really paint a realistic picture of what's happening. So we want to be looking at rollover of the girder. We want to be looking at torsional twisting deformations, strong axis bending, pre-stressing deflections, the effects of imperfections, and also the stabilizing effect of overhangs during transportation and handling. Beyond these kind of instability mechanisms, we also want to be evaluating new long span girder cross sections on their post-cracking strength. So not just linear elastic performance, but how do they perform after they've cracked? And beyond cracking and linear elastic performance, we want to also evaluate these girders on how well are they going to do during service life. If we have this new cross section, supposing it can get transported to site, can it still perform sufficiently well? And additionally, is it able to actually get transported to site? Is it constructible, and is it cost efficient? And so this project is kind of we've done some work on other projects as well. Professor Wiebe and Stanton had a previous project with another grad student of theirs that looked at developing buckling loads for long span pre-stressed concrete bridge girders, and I've been working with them the last couple of years on doing an imperfection sensitivity study and also analyzing the effects of cracking as well. So I do a kind of quick overview on lateral roll buckling and this kind of general instability behavior that we have. And here on the left is this girder that you can imagine is about to be picked up from a crane from above. And you can see here that this crane would be picking the girder up from a lifting loop that is at somewhat of an eccentricity from the kind of the center line of the girder. And what you have here is a lever arm between the center of gravity and the main weight of the girder at the middle and the reaction of the girder at an eccentricity off to the side. And as it stands here in this left picture, the girder is outside of moment equilibrium. So what it's going to do is it's going to rotate until it gets into moment equilibrium here in this center picture, where the reaction and the load are in line with one another. From there, though, there's going to be components of the girder's self-weight acting kind of laterally and vertically, which are going to, as you can see in this right picture, which are going to cause the girder to deflect more. And that additional deflection is going to cause the girder to be out of moment equilibrium, which will cause it to roll further, which will cause even greater components of the self-weight to be acting laterally and vertically. And this process will kind of continue in a negative feedback loop until it either stabilizes at a relatively low roll angle, or it will continue on until it buckles and eventually finds a stabilizing point in a post-buckled configuration. So that's kind of the general lateral roll buckling behavior that we're looking at, that we'll be examining new girder cross sections with. Now we've got a couple of other different instability mechanisms that we're looking at that I mentioned, and just kind of quickly going over like what they generally do. Strong axis bending. In the previous slide, I only looked at lateral weak axis bending, but strong axis bending would shift the center of gravity of the girder downwards, which is a stabilizing effect. So we'll be including those effects as well. And pre-stressing deflections are kind of the opposite. They, pre-stressing causes camber, which raises the center of gravity of the girder, which is a destabilizing effect. So those effects are pretty related. We'll also be considering overhangs, which, the negative moments of the overhangs kind of balance out with the positive moments of the midspan of the girder. And it really lowers the average deflection of the center of gravity and is a really very stabilizing, very stabilizing thing for girder lateral stability. We'll also be considering torsion and twisting, which, torsion essentially causes an additional roll, a little bit more twist along the girder at the middle, and it's a pretty softening effect that becomes even more prominent at higher loads and longer span lengths, and is destabilizing, and we'll be considering that as well. So now that we've kind of laid the groundwork for what we'll be looking for, let's kind of talk quickly about what tools we have to analyze new cross sections for long span girders. And the first is a numerical tool that we've developed called Rollbuck 2021. And this version is a linear elastic and uncracked model that essentially runs the schematic that I showed on this slide. Essentially does that, in a automated form. Essentially, a user inputs a shape of a girder, some loads, or an imperfection like that lifting loop eccentricity I showed. It rolls the girder until it is in, rotational equilibrium, and then it goes into this bottom loop down here where it deforms the girder, and then from that new deformed shape, it figures out if it needs to roll even more. And it essentially just does this loop over and over again until it comes up with a final converged shape. So that's one tool that we have. And then that looks at linear elastic uncracked sections. And we have this new tool that has been developed called Rollbuck 2022, which actually incorporates nonlinear material behavior and the effects of cracking. And it's really just a development of Rollbuck 2021, where the procedure is the exact same thing, but instead of using linear elastic relationships between moment and curvature, we instead develop these tables beforehand that tell us what the strong and weak axis moments are on the girder, or what strong and weak axis moments on the girder could be as functions of a bunch of different neutral axis orientations and curvatures. And then since we would know what the moments would be applied to on the girder, we can then figure out what neutral axis orientation and curvature exactly satisfies both the weak and strong axis moments that are applied to the girder. Using these tables, we can get back then into the original programming loop that essentially does that schematic that I showed a couple of slides ago. So those are kind of the numerical tools that we have. We've also developed a couple of analytical tools for predicting the final roll angle or final equilibrium angle of girders. This first is what we call the rigid link model, and a schematic of that is shown there on the bottom right of this slide. Essentially, we take the stiffness of the girder and the loads applied to it, and we boil them down into a single node that represents the center of gravity that is supported by springs of representative stiffnesses, like in the lateral bending direction, vertical bending direction, and torsional stiffness as well. And from there, we did a minimum potential energy formulation to come up with this equation form shown on the bottom left, which essentially is able to determine the final equilibrium angle of the girder based off of just a known applied load, the critical load, which we have formulations for, and the initial roll angle, which was that kind of middle picture shown on that slide a few ago. So that's one tool that we have, and it's conveniently it's able to handle all of the different types of instability mechanisms that I mentioned before, all in just this one formulation. The other model that we have is what we've called the simple amplification model, which you can get to from a couple of places. And you can come from the rigid link model by making a small angle assumption, or you can get it from a separate derivation from equilibrium paths and critical loads. And it's a simpler, more closed form model, but it allows one to very quickly and easily arrive at a prediction of what the final equilibrium angle would be. And this next picture is just kind of an example of these different tools matching up, which kind of shows that we feel confident that we can use these tools to analyze new girder cross sections. You know, it looks like there's only 3 curves on here, but there's actually 7 different ones. And that's because they're all predicting the exact same results. And what we're kind of looking at is what the initial roll angle, what the imperfections are basically amplified to on the horizontal axis as a function of different applied loads and their relation to buckling. So we have a good agreement between all of our different models, and we can use that for predicting what these behaviors are going to be like. So kind of stepping back out from there, what are the stability issues in longer and deep girders, and where do they come from? So we've kind of looked at what tools we have, but just kind of backing out, why do we have these issues? So as girders get longer and longer, to satisfy service loading requirements, you really need to develop deeper beams because of the increased gravity loading. But you know, it's expensive to develop new formwork and stuff in the fabrication process. So a lot of the girders are made deeper, but not necessarily wider by adding taller forms in the webs. So that really leads to lower relative lateral stiffness of the girders compared to the increased vertical stiffness, which means that as the girder tilts over a little bit because of possible imperfections, it's going to bend and roll a lot more than it will have otherwise, which leads to lateral instability issues, additional torsional deformations, that roll that we were looking at earlier. Additionally, as girders get longer and longer, there's more load, and as they're less laterally stiff, they're more susceptible to potentially cracking in the top flange corners as they're being transported and handled. So those are kind of some issues that we could see. And looking at this bottom bullet point here, these are just kind of a couple of different solution methods that we currently have for handling really long span bridge girders and making sure that they can get transported to site safely. We can increase the top flange width to make the girder have a stronger weak axis moment of inertia to make it harder to roll over. Or the best really good method for increasing stability is making the overhangs longer but you don't want to cause cracking to occur over the supports because of really long overhangs and big cantilevered moments. So you can also add some temporary top pre-stressing strands into the top flanges of the girders combined with overhangs to arrest cracking and really have a stable configuration that can be shipped to site. So kind of what's going to be our procedure for determining the optimal cross sections and modified new cross sections for long lengths? And really it boils down to a parametric study. And we'll be looking at different cross section options, which would include modifying existing cross sections with wider or deeper flanges or webs to see how do those girders perform with those changes to their cross sections. And then we can take the information that we've learned from that. We can test out different cross section shapes to see how they perform. Additionally, we could look at different material parameters in a parametric study, like the concrete density or the concrete strength, to see which one of those parameters really affects girder performance positively. And then, that could be something that we could recommend for focus on for development to really improve long span girder performance. And also we could look at some kind of more out there miscellaneous solutions like that aren't so much on the girder cross section, but more on other solution methods like temporary bracing, or maybe even something funky and weird like kind of putting a steel box or something like that in a torsionally susceptible area of the girder. But mainly we'd be looking at different girder cross section shapes and stuff like that. And we've done some preliminary work on this and gotten some results. So what you're looking at here.
Hank, can you please wrap up in a minute or so?
Yeah, sure, certainly. But anyways, just quickly say here then, not too much time to get into what we're looking at, but you can see that increasing the top flange width makes girders crack later and survive longer as they're rolled over, and adding temporary top strands makes girders perform a lot better as well. And then since we're kind of running out of time a little bit, look at some kind of logistical things we've been looking at as well. With current girders that we have, what are some maximum lengths that we can hit, not necessarily from stability, but because of logistics. As far as service loading is concerned, with current cross sections, we might be hitting issues with running out of space for pre-stressing strands at girder lengths of about 250 feet, or really importantly too, we might even be hitting weight limits with girders that are getting about up to around 250 feet with current girder cross sections with lightweight concrete. So even if you could theoretically make it stable, it might run into weight limits and stuff as well. But yeah, that's about it for the time. I'm happy to take any questions that you may have. Again, apologies for the screen sharing issues at the beginning of this, but hopefully you're able to see as well.
Yeah, no, we saw it. It was great, Hank. We will, because we usually always post the presentation on our website, we probably get back to you to get a recording of the presentation in a full screen PowerPoint. Okay. That would do it. One quick question, if you can please answer in less than 1 minute.
Yeah.
It's a question came out, and I would have the same question. Say, I thought that lateral buckling only applied to steel beams. Could you explain how it comes into the design process for prestressed concrete girders?
Yeah, that's a really great question, and I'll try to answer very quickly. And it really just boils down to what the support conditions are and what the applied loads are. So steel girders are, they're a little more slender, so their torsional stiffness isn't as high, but their self-weight also isn't very high. So you don't really see these rollover instability with steel girders when they're being lifted, but you do see lateral torsional buckling with steel girders when they're fixed at their ends, and service loading when loads are pretty high. But prestressed concrete girders, all girders are potentially susceptible to instability, and prestressed concrete girders have really pretty stocky and torsionally rigid, so they're not going to have LTB issues as much during service, but since they are pretty heavy, they're pretty susceptible to rollover during a lifting phase when their ends aren't restrained from twisting and rolling over. So because of their greater weight, prestressed concrete bridge girders might roll over during lifting and transportation and handling more so than a steel girder would. And a steel girder would be more likely then to twist and have lateral torsional buckling occur during service than a prestressed concrete bridge girder would. Hopefully that answers that question.
Thank you very much, Hank. It was great.